Okay, so I thought we would explore this idea of commutative operations and and look at a sketch of a proof that, in fact, that is safe. So the way I want to go about it is to look at a variant of a cell which provides the commutative operation that in unary form. So since the cell already has a value in it, that's one argument to the commutative operation that's been curried. So let me just stop there and see if what I'm saying makes sense.
Yeah, I'm glad that you were talking about that.
I have to admit, I'm not actually following quite just yet.
Okay, so the first thing is requiring to understand requires a little bit of background. You have to know what a cell is. So this is a design pattern that I sketched out prior to us developing wallets, and it's a process that supports getter and setter operations. So imagine that you've got a name or channel or location, depending on how you want to think about it. That's kind of that has a process wrapped around it.
Okay.
And then the process will accept two methods. One is get and one is set.
Okay. All right. So when we're defining cell, our definitions of cell is unique to how we're describing it in terms of our chain.
Sort of. I mean,
sort of.
The notion of cell is widely used in the industry. Mm-hmm. Our particular implementation is a little bit unique because it uses joins.
Okay.
So the idea is that you have a get and a set channel, and when you on the get channel, you receive a return channel where you're going to send the value, and on the set channel, you receive the value that you're going to set the value to.
Okay.
And so what you do is you after you receive that method, then internally, well, it doesn't matter whether it's internal or external. If you do a join on getting the do a join on getting the next request, whether it's a get or a set, and the state, where the state is the value. So I think Tomislav has posted a link to a Golang description of a cell.
Yeah, from tutorial.
Yeah, from the tutorial. Yeah. So it's fairly straightforward, right? The idea is that if you since you're doing a join, you can't get mixed up on the gets and the sets, right? If the join the getting the state acts as a kind of lock. So you have to have both the state in your hand and the next request.
Okay.
Because you have both things, another get or set is blocked until waiting on the state.
All right.
But
so go ahead.
I don't see join in this example, so I'm a little confused.
Well, in that tutorial, they probably did it a different way.
Okay.
Yeah. So in the one that I do, it's to illustrate the joins. So it's because joins act as a really cool way of doing locking. So does the basic idea make sense?
Yeah. Now I feel more oriented. Yep.
Cool.
Thank you.
Tomislav, do you understand?
Yeah. We basically want to ensure that only one, that we have something like mutable variable, but only one entity can change the variable.
At a time. I mean, you can have two entities that are battling back and forth, right?
Yes,
but,
at a
but,
time.
but at any given time, only one of them is going to. Okay, all right. So now we can extend the set operation, right? The set value operation to be any commutative operation on this domain of values. Why is that? So usually a commutative operation is going to be a binary operation. So if the let's say that we have a thing, a method or a message called update, and it provides a delta. Okay, so you might think of it as so an example of such a thing would be add. So add usually takes two numbers. Well, one of the numbers is going to come from the state, and the other number is being provided in the add message. Does that make sense?
Yes. So far, so good.
Okay, great. So then you can make add function exactly like set. Does that make sense?
Yeah.
Okay, so what add will do is it will receive the delta, and at the same, so it does a join where it receives the delta and at the same time it grabs the state. Mm-hmm. Since it's grabbed the state, it's not possible for anything else, any other update methods or anything like that to interfere with the execution of this particular method. Okay. So that's you can use the same locking mechanism. Okay, great. So now what we have to do is we have to prove that if we call add in sequence, you cannot distinguish that from add in parallel if you don't pay attention to the values. Or another way of saying that is that add in either sequence will result in the same final value in the state. Does that make sense?
Yeah, because it's commutative, whether it's serial or parallel, you're going to end up with the same result.
You'll end up with exactly the same result.
Mm-hmm.
Yeah. Tomislav, do you understand?
Yep.
Right. And so now it's the proof is almost self-evident, right? You run it forward in one order, and you get delta plus the original value in the state. You run so delta 1 plus delta 2 and plus the original value. And if you run it in the other order, you get delta 2 plus delta 1 plus the original value in the state. And so now you can see that since delta 1 plus delta 2 plus the original value is equal to delta 2 plus delta 1 plus the original value, that the result is the same.
Yeah, it makes sense.
Cool. And so now this works for any commutative operation that you add to a cell.
Can you also say that I mean this this value is like a monoid. So if we have like a monoid for this value, we can do this. Whatever this monoid.
Yeah, I mean it's automatically going to be, well, so we said commutative. I'm assuming that the operation is associative. And I'm assuming that there is an identity. So it is a monoid. This is kind of what we're really talking about. Is for any commutative monoid, this works. Or another way of saying is for any domain of values, which is at least a commutative monoid, this will work. So now what this means is that we can apply this when we're talking about merging two lists of COM events, right? Since we know if we are able to tell that the channel contains a value which which is an element of a commutative monoid, and that the operations, the messages, are commutative operations associated with that monoid, then we are free to merge by doing the sum of the deltas, or the sum is not as general as we would like it to be. The aggregation of the deltas. So you aggregate the deltas, and then you update the cell value with the deltas. And so now merge in a situation where you have two independent or isolated sources providing values to the same target, that's now mergeable. Before, when we had talked about conflict, the notion of conflict was stopped at the channel level and didn't descend into the value level. Does that make sense?
Yes.
So now what we're doing is we're saying there's an additional range of merge operations that we can do, where even though you have a conflict on the channel, if the channel contains a value that is that takes its if the channel contains state which takes their values from elements of a commutative monoid, then we can merge by doing the aggregate of the deltas and updating the value that way. So that's the core idea, and we can see from the math shows us that this is always safe.
There is one thing. So we are updating the channel, and we are doing some operation directly, like primitive operation, for example, plus.
The value has to be the operations on the value have to be primitive.
Yeah, I'm saying that we need to first realize what kind of operation we have.
That is absolutely
maybe this
correct.
Is a plus or yeah.
Yep. You have to be able to tell from the message that it is invoking this operation.
And how we can do this? Because basically we have some expression that can say different things. Maybe we extracted value v, and we are adding something.
Yeah. So again, at the level of types, you have to be able to know this information. It is a requirement for this to work.
Yeah.
Right. So you must be able to detect that these are the operations being done to this particular cell, which is a process that wraps around a channel. Or another way of, if you, it might be that the channel is used in something that's not quite a cell, but you're still able to merge. Yeah. So the other piece of the puzzle is that the thing that allows you to relax it from being a cell is that that there are not parallel consumers of those messages. There's only ever one consumer of those messages. Does that make sense? That's what the cell is doing for you.
Yeah, makes sense.
Cool. Yeah. if you cannot gain access to this information, that this is in fact one of the commutative operations available on the data domain, then you can't do this. You have to have that as input to this approach.
Mm-hmm. Yeah, for example, if someone is using to do the multiplication and then summing something, we cannot merge this, right? Because both operations we cannot really know.
No, as long as, so for example, on your cell, you could have an add and you could have a multiply, right?
Oh, okay, yeah. So we are doing one operation at a time.
You do one operation at a time, that's correct.
Mm-hmm. Basically, we need this to calculate delta, and then
that's
we know
correct.
what to do. Mm-hmm.
That is exactly right. You have to have all that information. Once you have all that information, then you are free to do this kind of merging.
Mm-hmm. So basically, now what we have in a non-negative number, we can look at in AST, and we can see that we are doing what kind of operation we are doing on this value before we are saving this on the before we are putting this in a cell.
Yeah. So in terms of applying it to Casper at the level of comm events, you're going to have a way of filtering or looking at the comm events to make sure that that you can gather the information that this isn't, that what's happening here is in fact the commutative operation on the domain value. If you can't calculate that from the comm events, then you're stuck. You can't do this merge. So I think this is going to be of use to us both now, but also in the future, because we can use type information to make this, to do optimizations. So the kind of optimizations I'm talking about are very similar to mouse motion collapses. Are you familiar with the mouse motion collapses?
I'm not sure.
No, I'm not.
So let's say you're writing a graphical user interface that is taking mouse motion, right? So for example, you're tracking the cursor. So let's say that when the user presses a button on the mouse, and as long as the button is depressed, the cursor changes to indicate that the button has been pressed, and while the user is moving it around, the cursor is in the depressed graphical feedback icon or image, and then when the user releases the button, then there's some action that is associated with the motion. All right, so can you picture that that situation?
Oh yeah.
Mm-hmm.
I remember you have this example also to say how sessions work.
Yeah, exactly. So now you can imagine that in this mouse motion situation, the user might do all kinds of wiggling of the mouse that has no real semantic import, right? So there's lots of jitter associated with the mouse motion that has no real semantic import, right? So for example, if they're dragging something from one place to another, all that's really interesting is the initial location and the final location. And the passage, with all the jitter is less interesting from a semantic perspective. Now, obviously, you want to give some kind of smooth feedback for the user in a situation like that. But we can imagine that if things moved fast enough, then the user couldn't even detect that you've erased the jitter. Does that make sense?
Yeah, yeah, very much.
Okay, cool. Then what we really want to do is just accumulate the meaningful updates, right? So you accumulate. So the real updates are the initial position and the last position. Likewise, in the case of updating with a commutative operation, you can collapse them all into a single event, which is the aggregate of the deltas. So that's kind of the idea, is that you can gather up all of the rights into a single right, which is just the aggregate over all of the deltas. And that will have significant optimization opportunities for us. And the reason is because you don't have to execute all those COM events. You just have to do one COM event. So all of those COM events can be collapsed into a single one. And that's very important. And in fact, in the case of history rewriting, so that everyone gets the same history, it's best if when you do this kind of rewriting, that it's marked as an aggregate event that is collapsing some number of other events. That way everyone can see in a log that this is what you've done. Does that make sense?
Yeah, for example, if we have some large list that we want to sum all the values inside, we don't really need to put all individual operations. When we are iterating the list, we can just at the end say, yeah, this is only one operation, updating to the final value, right?
Correct. That's exactly right.
Yes.
But also from the point of view of everybody sees the same thing, right? If there were some validators, for example, who were looking at the list from one perspective, and another group of validators that were looking at the list with a slightly different order, when this gets eventually logged to local storage in terms of state, the COM events that you want to see is the aggregate COM event. So that erases the history order, and so they all see exactly the same history, right? The one aggregated thing, and not different orders, and then have to calculate whether or not this is the same thing.
When you say aggregate events, what exactly you mean?
I mean the COM event, which is the update with the sum, as opposed to a bunch of different COM events, all of which are updates. Cool. That's all I wanted to talk about. Are there any other questions or comments about this?
This sounds like a nice optimization, definitely.
I think it is.
Yeah.
And again, the nice thing is that it's an extremely simple proof to show that it works, right? And we can, I mean, so that means we are again correct by construction, and we're using the whole framework to remain correct by construction as we optimize. So that's the other value add for this kind of thing. For our methodology, the correct by construction methodology continues to show off its value add again and again.
And we can basically maybe have some way of defining our own this kind of commutative monad type.
Yeah, exactly. So you just have to be able to detect that the value domain in the channel is the commutative monoid, and a way to show that there are messages against the channel that are using that operation, right? So you have to have both of those things. If you don't have both of those things, then you can't do this. So in the cell example, right, we have the add or more generically, the update method. Okay, all right. And I guess I can say, in terms of what we've been doing on the types side, a lot of our struggles and calculations have been how to get the container logic into the into Christian setting. And so far, what we seem to have what we seem to have come up with is that there's a fairly high bar for anything that is considered a container to be able to do this. Like you can't do this in general. You have to have a lot of already built-in information. So let me see if I can give a brief overview of what I mean by that.
And this is with operational semantics in logical form, or is this behavioral types?
Yeah, I mean, they're the same, right?
Same. Okay.
Yeah. The operational semantics in logical form generates a behavioral type system.
Okay.
Okay. So the logic that is generated from Christian's construction gets the container part of the logic from the fact that you've got a topos. So when you use plain vanilla Yoneda, you're going to the category set, and set is a topos, and because set is a topos, you can interpret your logical operations like and or and those kinds of things in the topos. If you wanted that container to be something other than a topos, so for example, you wanted it to be linear logic as opposed to classical or hiding algebras, then you need to use a variant of the Yoneda lemma, which is like an enriched version of the Yoneda lemma. So instead of going to, and what this does is it ultimately requires that your structural theory, in other words, the theory of computation that you've got, the syntactic part of your theory of computation, be enriched in whatever structure you want to put on your container. So the example that we've been going with as the one that is kind of filters out, separates the wheat from the chaff, is that the container is linear logic. So that means the conjunction splits into two and the disjunction splits into two. Another way of saying that is that your logical operators are resource aware. So the tensor operator is aware that when you combine resources, it's not necessarily an idempotent operation. Again, in classical logic, if I say A and A, that's the same as A. So it is raining and it is raining is the same as it is raining. But it is raining in Seattle and it is raining in London. These are not the same. There are there are resources associated with Seattle and London, that separate these. Even more directly, Alice has $1 and Bob has $1. Then we're talking about potentially $2 in the total sum of all the resources. So linear logic takes care of this resource awareness. So we want to use that as our sort of paradigmatic alternative container to sort out these various constructions to see if they are nice with respect to swapping out the container. So again, the idea is that, you know, we have some logic that accounts for the spatial part of the theory. So from term constructors like, you know, the par constructor or the for comprehension or the output, we can generate formulae. So in the same way that you have process P par process Q, then you could imagine that phi is some type or formula of which P is an inhabitant, and C is a type or formula of which Q is an inhabitant. And you can form the formula phi par C, and then P par Q would be a witness or an inhabitant of the composite formula. So that's the spatial side of the construction, right? So it's lifting term constructors to formula constructors, and now we want to move. We want to look at just the container side. So operations like and or implies. So that would be like phi implies C or phi and C. Those kinds of those are examples of formula we construct using the container side of the logic. So when we move to a different container, one that is not classical or intuitionistic, then we have a container that, as an example, would be linear, right? So containers that are aware of resources. And if you want some intuitions to have in your mind, you can kind of think of a relational storage, which only allows reads, and the reads are you know, the values are stored persistently. You can't take them out of the database. Then that's very much like classical or intuitionistic logic. You can think of the container part as our storage mechanism. And when we move from the classical to linear, then our storage mechanism has the ability to be updated, and we can be aware that some of the data in the storage actually, you know, it cost us to put it in there, and it can cost us to take it out. So that's one set of intuitions that might help you think about the spatial side of the logic that we're generating from the container side, and why linear logic might be an important or useful container. So then the next piece of the puzzle is to look at this this enrichment idea. And what it forces is that the theory of the syntax, so the spatial side, has to be enriched in the theory of the container. And that turns out to be a fairly high bar. So in the case that we're talking about, you know, so you have some theory of computation like lambda or rho or pi. What you'll do is you'll take the category that is associated with the category that's associated with the syntax. So there's a Levier theory there that is capturing the syntax, and there's some category that is associated with that Levier theory. And now what we want to do is, so this is a one with finite products. And what we want to do is enrich it in such a way that it becomes a container for linear logic. Now, there are, like, one might think, for example, that Valeria de Paiva's dialectic construction would do the trick here. So we start with some category with finite limits. So we would have to adjoin pullbacks and equalizers, I think, to the Levier theory to get something with finite limits, and then generate something that interprets linear logic. But in fact, it turns out that de Paiva's construction actually depends on the category that we start with having being Cartesian closed. So it's already got a notion of it's got a notion of function or lambda already embedded in it, in order to get de Paiva's construction of linear logic to be rich enough or faithful enough to support the full range of formulae that we would like to support. So what that says is that at least going down the path that we've investigated, that already the theory, the spatial side, has got to contain a lot of the container logic inside it. So it's not modular in the way that we would hope it would be modular. So we're kind of taking a step back and looking at what's going on with this syntactic presentation that I've been able to construct in a fresh proof theory for Ladle, where I look at the proof theoretic side and I make some specific assumptions about the theory of computation, and then use the resource and reflection tricks to turn the operations into a tensor, basically a monoidal category. So I can get a monoidal category if I make certain assumptions about the theory of computation. So that's kind of that's what we're doing. I know this is a lot of information to take in, but any questions about this?
When you say that there is already something like lambda inside, are you referring to some kind of nominal theory that is already inside? Because I remember that you compare this two things.
It's not necessarily nominality that's the issue. The issue is that it's got to somehow be, Cartesian closed. It's got to be closed. You have to have some kind of function notion of functions. It's got to be functionally complete. I mean, that's of course just to run Valeria de Paiva's construction, the dialectic construction. But it's not clear that you know, I mean, there's no proof that there isn't some other construction that would do it without this information. But certainly of the ones that we can see, that, you know, we have ready access to via, you know, easy Google research, it's not, it does feel like, in order to get the linear situation, you're somehow assuming that the initial situation is Cartesian closed, and that's unfortunate, right? Because it's not. It means it's not modular, right? You've already got the container. You've already got the container information somehow in the structural information. So that's and the desiderata are that the container and the theory of computation are at least initially disconnected. And then of course we know that if you do have a Turing complete model, then you can build things like lists, right? So we know how to build a con cell in lambda calculus. We know how to build a con cell in the pi calculus. So you can build these container structures when you've got a Turing complete model of computation. But the fact is that we're only representing the syntax, not the semantics. So if you want just a syntactic account, the thought was to only go as higher order algebraic theories. So you've got some exponential objects, but you don't have all of them. So for example, in the pi calculus, the names are exponential, but not processes. So it's a lot of work to try to get this thing at the level of generality that we want with all the desideratum.
Yeah.
It is really but it may just be that this is a critique of Christian's approach, right? That Christian's approach does not readily yield this kind of modularity. That it works for topoi, and that's kind of it. So yeah.
And you mentioned Quantal as one of the options for collection.
Yes.
And
yes.
I'm wondering this ordering in Quantal, how this is connected to something useful for linear logic, and why?
Oh, sure. Well, the basic. So when you're interpreting linear logic in quantals, you're looking at it. These are special quantals. They have extra structure. So you're going to have a dualizing object, and you'll have a co-free comonad to model the exponential operatives. But at the most basic level, the tensor of the quantal is going to model the tensor of linear logic, and the join of the quantal is going to model the with operation. Sorry, yeah, I think that's right. The with operation of sorry, no, it's the plus. Yeah, the plus operation. My mistake. The plus operation of linear logic. So if you have the tensor and you have the plus from linear logic and you have a dualizing object, then you've got all of multiplicative and additive linear logic. So that's where it's coming from in the quantal structure.
I see.
Tensor maps to tensor, plus maps to join, and Bob's your uncle.
I see. So if I remember correctly, you said that in Quantal we have sets of traces. So basically
sets of sequences, yeah.
Sets of sequences of traces.
No. The traces are sequences.
Oh, yeah. I see. Oh, yeah, and with that we can encode this additional, basically information that we need.
The sequences are words in a monoid, right? So that's giving you your tensor operation.
Oh, I see.
And the set operation, so the set union is giving you your join. And the dialectica construction is, even richer in terms of the kind of quantole that it generates. So it's going to generate a category that interprets all of these operations. So you can extract the quantole, but you're also going to get, there's other stuff lying around in the category that can facilitate, for example, the interpretation of proofs and not just formulae. Coolio. Thanks so much for all your time and attention and good questions. And I'll see everyone in stand-up in about 10 minutes.
Greg, if you can get this video out quickly, because the first part of that, Not Zipper might want to listen to relatively quickly.
Sure.
Thank you.
Mm-hmm.